Okay, so this is the last example problem of Unit D2, example page 7. Let's remember earlier in Unit D2 we looked at water jet turbine analysis. So I want to probably begin once again with the video. So let's just take a look at once again the video of water turbine. You're going to inject the water jet and it just starts turning, and once you turn, you keep injecting the water, keep it turning. Okay. So the previous problem, example problem, we looked at how much force is developed. Okay, so this is a previous example. Okay. So this is a previous example problem. We looked at, okay, how much force is required in order to anchor this turbine vane in place. In other words, it's equal and opposite to the force developed by impinging this water jet and hitting to the turbine. That was called anchoring force, and equal and opposite to how much force is developed by this jet. Okay. Now, what if, after the turbine starts spinning, you just keep injecting this water jet and keep that spin? So after this water jet turbine starts to turn, okay, so how much force do you need to maintain spinning? Okay, so this is the second stage, step number 2 solution of the water jet turbine. Let's take a look at the problems. Okay. This is a vane on wheels, which is kind of odd expression, but let's move on. A vane on wheels moves with constant velocity p0 when a stream of water having a nozzle exit velocity of v1 is turned 45 degrees by the vane as indicated. Well, in this case, 45 degrees. Note that this is the same moving vane considered in previous example. Determine the magnitude and direction of the force F exerted by the stream of water on the vane surface in order to keep this vane moving. In other words, water jet turbine keeps spinning. You need to develop certain amount of force to keep it spinning. Okay? The speed of the water jet leaving the nozzle is 100 feet per second. The magnitude of this velocity is 100 feet per second. And the vane is moving to the right with a constant speed of 20 feet per second. Okay. So this is a little bit more explanation of the problem statement. So this is water jet turbine as you saw in the video. Okay, water jet turbine has a bunch of turbine vanes, and as you inject the water, hit the vane, creating the force, then once the turbine starts spinning, it just keeps spinning. Okay, so this is essentially approximation of this into a linear motion. In other words, this is actually rotating motion, but in a small segment, you can approximate this into a linear motion of V0 of this turbine vane. So let's flip-flop it, and then let's just put the imaginary wheel. It's just imaginary because this turbine vane doesn't come with wheels. Okay. So suppose if you approximate this spinning as a linear motion V0, using imaginary wheels. Then this happened to be 20 feet per second. So spinning speed, approximated as a linear translation, 20 feet per second. Water is coming in with 100 feet per second, hit the vane and deflected 45 degrees. Now under this situation, how much force are you are you developing to keep moving this turbine? Okay? That's what we are interested in. So, this is a fairly similar solution process against previous example. So I'm going to begin with coordinate system x and z. Z is of course elevation, which is the opposite direction of the gravitational acceleration. So this is my coordinate system. And then obviously, as you imagine, as this turbine vane moves linearly, translating to the right, you have to deal with rolling resistance, which is the force developed by resistance. Let's call this resistance force X. And then in this case, I know exactly which direction is the resistance force is. It's opposite to the force developed to the positive X direction. And also, you have to deal with reaction force. This R is a reaction force in Z direction. Okay? So rolling resistance and reaction force, X and Z direction both. So those are the forces you need to include in this analysis here. Okay. So how can I solve this? And it's one of the difficulties here is this thing is moving with a constant speed, 20 feet per second. If you choose fixed control volume doesn't move, but the turbine is moving. So essentially, turbine is moving against control volume. So what is the best choice of your control volume? Of course, moving control volume. Control volume which is surrounding this turbine vane, moving with the same speed of this turbine vane. That's called moving control volume. Let's choose that. Okay, I'm going to choose that. This is a control volume including the turbine vane. And then this control volume is moving to the right with the same speed of this motion of the turbine vane in X direction. Moving control volume. Okay? Moving control volume comes with the velocity of control volume itself. Let's go back one page. Okay. So let's just take a look at, again, how can we handle moving control volume. Moving control volume is the one that control volume itself is moving with the velocity VCB. Okay? So if you choose moving control volume, you have to use W, the relative velocity, in place of velocity, which is usually absolute velocity V, but you can't use that. Okay? So how can we find out relative velocity? Well, this is again same thing we did in unit C1. Unit C1 was moving control volume. This one, no. Unit C1 was deforming control volume. Unit D1 was deforming control volume. Unit D2, we are going to look at moving control volume. Essentially the same thing. Okay, so this is absolute velocity V. This is the velocity of moving control volume. This is a relative velocity. Okay. So W plus BCB is equal to B. So how can we get the W? Well, of course, W is equal to B minus BCB. No. Actually B. Flip-flop the CB and add. Right, remember? This is the B. Flip-flop BCP. then add them up to obtain W, right? So this is how you obtain relative velocity. So let's think about relative velocity here. Okay? So this is absolute velocity. Well, I skipped a few processes, I'm so sorry. I'm going to define control surface 1. I'm going to define control surface 2. I forgot this process. Control surface 1, because you have outward the unit normal vector in 1. Control surface 2, outward the unit normal vector in 2. This is the incoming velocity v1. This is outgoing velocity v2. Now v1, v2, those are absolute velocity. This is a moving control volume, so we cannot use absolute velocity. Now using relative velocity instead, I'm going to go back again to the previous page. One of the beauty of using moving control volume is this is now the momentum. Something is completely missing, which you usually see something here. This is the time rate of change of momentum within the control volume is dropped off. What do you mean by that? Well, suppose if this is a fixed control volume, large fixed control volume, then this is a turbine blade with an imaginary wheel, and it's going to move and move and move. Eventually get out of fixed control volume. Okay? If you do this, this is the equation. dt integral CB B rho dB plus integral CS B rho E dot n dA is equal to summation of the force. This is going to be probably, you can never solve it. It's going to take forever for your analysis. You probably cannot solve it. This is impossible, near impossible, I have to say. Because within the fixed control volume, this is going to be keeps changing. Position here, position there, position there, position there. You keep track of this value at every single position. As this one comes in and comes out, this term keeps changing. Now forces also keeps changing as you move on. Okay? This is one single nightmare problem you basically invite to you. Why this is such a nightmare? Because you're going to deny Reynolds transport theorem. You basically terminated Reynolds transport by using this large fixed control volume, because if you allow this turbine bay move within a large fixed control volume, this is essentially within this large control volume, you're going to do Lagrangian analysis, right? This is essentially, you are going to define Lagrangian analysis within a large fixed control volume. It is essentially the reverse process of Reynolds transport theorem. You are going to essentially kill yourself. This is a suicide in fluid mechanics. You basically kiss goodbye to Professor Reynolds saying, hey, I'm basically making your Reynolds transport theorem totally meaningless. Let's not do this. Okay? So how can we avoid this kind of thing? Oh, moving control volume. What is the great benefit of moving control volume? Of course, if you choose moving control volume, okay, obviously you have to deal with W at each control surface here and here. However, This is the equation. W rho W dot n the A is summation of force. Oh, wait a minute. This is the, well, it's a quite a bit different equation. What's the difference? I don't have this term here. Why? Because if you choose moving control volume, you essentially turn your analysis into steady state. This is a moving bay. So if you let the bay move within your fixed control volume, this is a big unsteady state Lagrangian analysis. Near impossible to solve. This one, you can solve it now as an example. This one, you probably spent 10 years, pursue after your PhD dissertation maybe, and then you basically gave up and can't graduate kind of thing. Okay? So this is near impossible to solve. This is example problem right now. Okay? So it's a big difference, huge difference. I have to tell you it's going to be a huge difference. So choice of control volume. Of course, you can choose any control volume, but if you do a poor decision, you're going to introduce more complication. Now, this is the ultimate choice of complication introduced to you. You're going to deny Reynolds transform. Anyways, so we are going to apply this equation for moving control volume. That's good. Okay? Now, one of the challenge here is let's find out relative velocity right here. So, W is a relative velocity. Even though this is relative velocity means if you are standing here, moving together with your moving control volume, seeing this V1 incoming to you, what is the velocity you feel? That's called relative velocity. Relative to the moving frame, which is attached to the control volume, moving together with it. So this is going to be Wx in x direction and Wz in z direction. Let's be careful about that. Okay? So you want to find out W1 and W2. So let's do that. Okay? So this is control surface 1. Right here. Okay? You have velocity incoming V1. Okay? You have, this is a BCB. This is the velocity of moving control volume. Same as that. What is W? Well, W is B plus flip-flop CB and add, flip-flop this. So flip-flop it and add them together. If you add them, you ended up having this much. This is W1. So what is W1? Well, W1 is magnitude-wise B1 100 feet per second, subtract 20 feet per second. So this must be 80 feet per second to the right. Right? So this is essentially W1xi plus W1zk, but this is 0. Even though this is a relative velocity, this is still only in x direction. Okay? W1x magnitude is 80. Alright. So this is relative velocity at control surface 1. We found it. Okay. So let's use this W information within this equation, W and W. Okay. So let's apply momentum equation. Keep in mind, this is a momentum equation for moving control volume. Okay? Integral over the control surface W rho W dot N dA is equal to summation of the force. Of course, this one steady state equation to begin with. Okay, you have x direction called x momentum. Okay, integral of control surface 1 W1 x direction. This is Wx of control surface 1 W1x. Maybe I should say Wx1. No, it's okay. W1x. Rho is the density of water. W dot N. W dot product. Dot product against N1. W dot product against N1. This is going to give you minus of W1, which is W1x. But anyway, this is going to be W1 dot product N1. Okay? dA1 plus integral control surface 2 W2x rho W2 dot product N2 dA2 is equal to summation of the force in x direction. The force is only one, Rx minus Rx. Okay. So this is a rolling resistance force in x direction. Z momentum. Integral of control surface 1 W1Z rho W1 dot N1 dA1 plus integral over control surface 2 W2Z rho W2 dot N2 dA2 is equal to the force positive RZ. So this is x momentum, z momentum. I'm going to apply also continuity. Continuity, this is integral CS rho W dot N dA is equal to 0. Okay. Again, continuity is already steady. So this is going to be very simple. Again, density cancels out. This is constant body, it's water, goes outside, goes away. This simply tells you W1, the magnitude, cross-sectional area A1 is equal to W2, the magnitude, cross-sectional area A2. The same thing. This is essentially Q1 equal to Q2, right? In terms of relative velocity. Same meaning. Okay? Let's do the same analogy here. If the cross-section area of incoming stream doesn't change and gets out at outflow, in other words, cross-section area of water jet is constant. If A1 equal to A2 is equal to A, then W1 equal to W2. W1 is a magnitude of this, which is 80 feet per second, which is equal to W2. Magnitude of relative velocity at exit is also 80 feet per second. Let's call this W. Oh, this is a really nice result from continuity. So I'm going to combine this continuity together with X and Z momentum, and let's finish up the solution. Okay, so X momentum. X momentum now becomes Rx is equal to W, which is W1 equal to W2 equal to W, 80 feet per second, W square rho A, cross-section area is A, minus W square cosine 45 rho A. Okay? So I hope you can do this. W1x is W1, which is W. Rho is rho. Dot product is minus W1, which is W. Cross section is A. Brought to the right hand side, minus value, so it's positive. Okay. This one is W2x. W2x. W2x is this is a W2x. This is a W2z. Okay. This is 45. So W2x is W cosine 45. W2.N2 is just a W2, which is W. Density is rho. Cross section is A. This is positive, but it's going to be minus sign comes up. Okay, so I hope you can do all of those. I'm not going to show you details at this point, but so let's just plug in those values. W is 80 feet per second square. Density 1.94. So that's per cubic foot. Cross section area 0.006 feet. Minus W again. W again. 80 feet per second square. Cosine 45. Density 1.94. Cross section area 0.006 feet squared. Okay. You can conclude Rx is equal to 21.82 pounds. Let's do the same thing for Z moment. Z momentum, interestingly, W1Z is 0, right? W1Z is 0. W1 is only in next direction. W1Z is 0. So this whole term drops off. So only this term remains. W2Z. W2Z is W2, which is W as a magnitude, sine 45. Rho is rho. W2.N2 is just a W. Cross section area A2 is A. So you can say Z is equal to W square sine 45 rho times A. So let's just plug in W is equal to 80 feet per second square. Sine 45 degrees, density is 1.94 slugs cubic foot. Cross section area 0.006 feet square. I actually realized this must be square, sorry. This is area. Sorry for that. So this is going to be what? 52.68 pounds. So now I got Rx and Rz. So let me just finish up the analysis here. So essentially what I got here was, let me just erase this guy, and more accurately draw. So Rx is equal to 21.82 pounds. Now Z equal to 52.68 pounds. Okay. So these are the essentially reaction force. So the force developed by impinging this water jet to the turbine vent is equal and opposite to this reaction force. This is the reaction force. Okay. So magnitude of reaction force is square root of Rx squared plus Rz squared, which is 21.82 pounds squared plus 52.68 pounds squared. So of course you know this is the magnitude of reaction force 57.02 pounds. So this is magnitude of reaction force. So the force developed is exactly equal and opposite to this reaction force. Of course you can determine the angle here, this angle. So this angle is inverse tangent of 52.68 pounds over 21.82 pounds. So this angle here, the direction of reaction force is 67.5 degrees. Okay? So this is how much reaction force developed due to the impinging water jet. So if you take equal and opposite to it, it is going to be a force developed on this turbine vent. And also you can tell the direction of that force also. So that is the force required to keep spinning this turbine. Okay, after you start up and kick up the turbine, you keep supplying this much force to keep the turbine keep spinning. Okay? So, most important thing is, without moving control volume, this could be a nightmare problem. You can never solve it, usually. So let's be careful, what is the right decision for your control volume? Control volume is, again, it's just a arbitrary choice. You can do horrible decision. Or you can do a smart decision. Okay? So let's be careful about that. Alright, let's stop.